The Earth does not always give up its secrets easily. Paleontologists may have to spend many long hours, days, months, or even years hunting for fossils, sometimes with no luck at all. As a micropaleontologist, I can't physically hunt down my fossils in the field, they're way too small, but I have logged many hours carefully preparing, dissolving, separating and concentrating fossil residues from rocks I collected, excitedly transferring them to a microscope slide to find nada, zilch, nothing. Often when the fossils are found, they are either poorly preserved or fragmentary. Frequently, one is presented with a jigsaw puzzle that takes dedicated workers months, sometimes years to fit together again. But sometimes, just sometimes, we strike gold. Let's let Nick Pyenson tell us about one such find.
What I love about paleontology is that it's fundamentally about discovery. Discovery in the world out there. You never know what you're going to find. For the site in Chile, we just happened to be at the right place at the right time. We heard about this unusual site called Cerro Baena many times before, and one of our colleagues brought it to our attention because it was being exposed by a road construction company. What we're talking about is a site that's about 3 football fields in size, covered with the skeletons of fossil whales. The skeletons were exposed right next to the Pan American Highway, so there's 18-wheelers, large road equipment going by all the time, creating vibrations that can actually damage and destroy the fossils. Our job is to preserve as much information as possible, and we had precious little time to document anything scientifically relevant about how those skeletons came to rest. So I remembered that before I went to the Atacama, I had met 2 people, Adam and Vince, roaming around the halls here in paleobiology, and I thought, I wonder if their grab bag of digital tools would help us.
So we met Nick years ago in the basement of the Natural History Museum when we were digitizing a dinosaur fossil. He stopped by to see what we were doing, and we talked for 20 minutes, and then we didn't hear from him for over a year. Suddenly we got a panicked phone call, and he wanted to bring us down to Chile within a week. And so within about a week, we found ourselves on an airplane with all of our equipment heading to the desert in Chile.
I think within maybe 30 minutes of our plane landing, we were on site and we started 3D scanning. We basically just threw everything we had at the site because we knew we only had 5 days.
We really developed different workflows and different kinds of ways to document the whale skeletons before us, using a variety of digital techniques, because nobody had ever done this before. There was no field guide about how to use 3D in this context.
One of the exciting things about documenting something in 3D on location in another country using new technologies is that you don't know exactly what you've captured until you get it back into the lab and you get to process everything.
Now that we've scanned the site, we can actually bring that site back. You have to remember, this site no longer exists.
We can translate it into a variety of outputs, one of which is 3D printing. And what's very exciting is that we're going to be able to print one of the best preserved fossil whale skeletons. When done, it will be the world's largest 3D print of its kind.
When you've documented something in 3D as thoroughly as we have, the cool thing is that we might have the information to questions that scientists haven't yet had the opportunity to ask.
So taking Adam and Vince down to Chile was a bit of a leap of faith, but that hunch proved to be correct, I think, in the long run, because what they've done is shown me what 3D can really do under the right circumstances, in the right context, with the right need case. With Cerro Baena, it was clearly the right thing to do.
As I told you, pure paleontological gold. And isn't it incredible what technology allows scientists to achieve today? An entire paleontological site now preserved electronically, even though the original quarry is now paved over. We will return later when we see what this fascinating study has revealed about these incredible fossils. But for the rest of this episode, I would like to consider, why would creatures that evolved on land move back into the ocean? Which group of mammals would throw away their legs for the sea? And finally ask, how can we explain the wonderful paleontological treasure at Cerro Baena? Since we started to consider animals scientifically, comparing them to other creatures in the animal kingdom, it was abundantly obvious that whales, or cetaceans to give them their scientific name, were mammals that probably had ancestors that lived on land. We see features such as the bones in flippers that very closely resemble the limbs of land mammals, a vestigial hind limb, a vertical movement of the spine when swimming that shares more in common with a mammal running than a fish swimming, and, of course, the fact that whales need to breathe air. All of this suggested a land-animal link. But why make the move back to the water? If you've watched my other show, A New History of Life, you will know the difficulties vertebrates had to overcome in leaving the oceans and adopting a life on land. One of the most obvious problems was how to obtain oxygen from air rather than water, but there were other hurdles too. There's the need for a more robust skeleton that would make up for the buoyancy effects you no longer enjoyed on land. Also, there are adjustments needed to accommodate hearing in a gas environment rather than a liquid. Of course, there is the necessity of developing limbs rather than fins to get around. In A New History of Life, we identified a fish that was pre-adapted to make this break for land, Eusthenepteron, and Tiktaalik, a vertebrate in transition between fish with fins and a tetrapod with limbs. In that series, we also described an array of early tetrapods like Acanthostega and Ichthyostega, and some of the first reptiles like little Westlothiana, which, with the evolution of amniotic shelled eggs, would finally break ties with the aquatic environment. So, given all the challenges vertebrates faced and adaptations they evolved in making the break for land, it might be a surprise that some of them return to the water, some so completely that they can no longer survive on land. Several groups of vertebrates have made this profound move, but why? At this point, we must be cautious with the language we use. It is very easy to give the impression that there is some sort of teleological motivation driving evolution. It is important to understand that evolution does not have a goal in mind. It is not a matter of design. Creatures will be selected for in particular environments as environments change based on certain physical and biological shifts through time. The characteristics or mutations that organisms possess are not produced because they choose to evolve things like flippers or echolocation. These features evolve through natural selection over long stretches of time. To expand on this a little further, let's consider the theories of one Jean-Baptiste Lamarck. Lamarck was born in northern France in 1744 and had an early career as a soldier. His career path would change though, and he became quite a noted naturalist. He lived during interesting philosophical and political times and would witness the French Revolution, potentially a little worrying as he did come from an aristocratic family, even if it wasn't all that well to do at the time. He was appointed as the keeper of the Royal Botanical Gardens and, very tactfully, changed its name from Jardin de Roy, Garden of the King, to Jardin de Plantes at the height of the Revolution. Early in his career as a naturalist, he believed that species were fixed, but would later change his views, coming to believe in the transmutation of species over time. Lamarck, although not the first to consider some form of evolution, was one of the first to come up with a reasoned process to explain how it might happen, what today we call the concept of Lamarckian inheritance. His hypothesis suggests that creatures pass on characteristics to offspring that they have acquired over a lifetime. Let's consider how Lamarck believed species could change over a lifetime with a little help from this giraffe. In the Lamarckian view of evolution, giraffes got longer necks as they stretched to reach high leaves in high trees. This tendency to generate longer necks would then be passed on from generation to generation. In contrast, a Darwinian view, though, would state that giraffes that were born with slightly longer necks would have a selective advantage if they were feeding on tall trees. Over time, natural selection would favour those giraffes in this tall tree niche with longer necks, and over time we would see the evolution of the giraffe as we know it today. It is important to understand this while we consider the evolution of cetaceans from their land-based ancestors. The proto-whales did not consciously move back into the ocean, forcing their own evolution in some way. Rather, certain forms would have a selective advantage, allowing them to inhabit increasingly more aquatic environments in a step-by-step manner over millions of years. This story is now all the more fascinating as, in recent years, many wonderful fossils have been found that have turned mere speculation about the evolution of cetaceans into a true, well-documented family history. So which group of mammals would start the whales along a path to the ocean? Genetically, we know that whales fall into a group of mammals that are called the even-toed ungulates, or the artiodactyls. The Artiodactyla includes familiar modern animals like pigs, camels, the giraffe and deer, but the closest land-living relatives of the whale today is the hippopotamus. Please note though, this is not suggesting that whales evolved from hippos, rather they share a common ancestor somewhere in the biosphere's past. This concept of a common ancestor is often a source of confusion for some, particularly with regards to our own biological status. Specifically, we and our closest living relatives, the chimpanzees and the bonobo, all both share a common primate ancestor back in Earth's history. Humans did not evolve from chimps. But getting back to the whales, who is the best paleontological candidate for the common ancestor in this case? To answer this question, we need to roll the clock back to around 54 million years ago, about 12 million years after the death of the dinosaurs, during the early Eocene, and in a region of the planet defined by the Tethys Sea. Back then, the Earth was much warmer than it is today, and climatically more homogeneous, with less difference in temperature between the equator and the poles. Fossils of tropical species of palm and crocodiles are found at quite high latitudes. The early Eocene environment had just come off the heels of the Paleocene-Eocene thermal maximum, which was the warmest period of the Cenozoic, just 2 million years earlier. The Eocene world had started to look a lot more like the planet we are familiar with today, with continents and oceans in the familiar position and a widening Atlantic Ocean. And India was starting to collide with Asia, building the Tibetan Plateau and the Himalayas. And on India, a small herbivorous deer-like creature, about the size of a raccoon, could be found living along the edge of rivers and lakes in an area not far above sea level, but which is now elevated high in the Himalaya mountains. This creature, about 2 feet long, is Indohyus, a member of a sister group of the cetaceans called the rheulids. Most paleontologists now agree that it was from animals like this that the lineage that would give rise to modern whales would evolve at about 54 million years ago. Now, why do we presume a cetacean relationship with this little beast? It certainly doesn't look like a whale. There are, though, similarities. For example, the auditory bulla, the bones that surround the inner ear, are very distinctive, adapted for hearing underwater and only shared by this group and the cetaceans. In addition, the bones of Indohyus are thickened, not unlike modern hippos, an adaptation that semi-aquatic animals possess to help them overcome buoyancy effects and allow them to stay underwater. You could imagine this little creature probably moving relatively slowly on land, but diving into a pond or river to escape predators or nibble on aquatic plants. So if Indohyus, or a creature very much like it, gave rise to the whales, who was the first true member of the whale lineage, the cetaceans? Allow me to introduce Pachycetus, so far the oldest member of the cetaceans for which we have fossil evidence. We are now around 50 million years before present, and the little herbivorous deer from which the whales evolved has grown to about 6.6 feet long, and this creature has also developed a taste for meat. It lived on the shores of the Tethys Sea in what is now northern Pakistan. Pachycetus lived in a freshwater floodplain environment, but was likely a relatively poor swimmer. It might have waded through shallow water, ambushing animals that came to the water's edge to drink. This creature still doesn't resemble modern whales, but in addition to the whale-like features present in Indo-Hyas, Pachycetus is starting to develop an elongate whale head. Our next fossil whale is Ambulocetus, or the walking whale, dated to about 49 million years ago. Although a little larger than Pachycetus, about 10 foot from tip to tail, Ambulocetus fossils demonstrate an important change in the cetaceans. They are now starting to inhabit marine in addition to freshwater environments. The move to the oceans had started. Another important feature is the presence of a large mandibular foramen. In modern whales, this area of the jaw is filled with fat and helps pass sounds to the inner ear, an important feature for hearing underwater. Less than a million years later, evolution has continued to shape and alter the cetaceans. This is Remingtonocetus, a member of the family Remingtonocetidae, a creature that is found in more diverse marine environments than its older relatives, with fossils being recovered from nearshore and lagoonal sediments. Its limbs are shorter than previous cetaceans, and although it may have swam in the doggy paddle style used by Ambulocetus, it may have also started to undulate its spine in an aid to swimming. Let's pause just for a minute. Ever considered how you manage to stand up? It's actually a complex interplay of many parts of your physiology and anatomy, but a vital part of the hardware of balance are the semicircular canals in the inner ear. These are 3 tubes filled with a liquid that moves as you move your head in various directions. The liquid moves hairs in the canals that trigger nerve impulses to your brain, giving you an idea of the motion you're experiencing. These motion detectors are particularly important if you are an active creature moving around on land. And this brings us back to our whale story. For another interesting feature of the Remingtonocetidae is a reduction in the size of their semicircular canals. In a paper authored by Fred Spoor of the University College of London and others, it was stated that this change in canal size indicates that these creatures had reached a point of no return. The cetaceans from now on were destined for an aquatic or at least semi-aquatic existence. At around 48 million years ago, and probably living alongside the Remingtonocetidae, we find fossils belonging to Protocetidae. Unlike the fossils that we've described so far, they are only found in India and Pakistan. The Protocetidae have a far greater global distribution, including Europe and North America, and were probably swimming freely through many of the globe's tropical oceans. As you can see, the Protocetidae, such as Protocetus here, are becoming much more whale-like, with the possibility of the development of a fluke, a 2-lobed tail in some species, and the migration of the nasal openings to the top of the skull. 4 species of the Protocetidae, which may have still been semi-aquatic, moving around on land would not have been graceful, probably akin to the way modern seals move today. But for the next stage in whale evolution, we need to move to the USA, and some interesting fossils recovered from Arkansas and Alabama. In 1843, vertebrae belonging to some fossil animal were sent to the American Philosophical Society in Philadelphia and described by Richard Harlan. Initially, these findings were identified as belonging to a Mesozoic marine reptile. This may in part be due to the fact that marine reptiles like mosasaurs and pliosaurs had recently been described in Europe. Accordingly, Harlan gave his find a reptilian suffix, Basilosaurus, meaning king lizard. In 1839, the famous British anatomist Richard Owen, who would later go on to found what is today the Natural History Museum in London, correctly identified the fossils as belonging to a mammal. He wanted to rename the beast Zeuglodon, meaning yoke-tooth, but the rules of taxonomy are strict and the first name has precedence. About 10 years after the initial description of Basilosaurus, Albert C. Koch, a fossil hunter, and it would appear a man who had the element of the showman about him, travelled to Alabama to find more fossils. He collected a range of material, including a basilosaur skull, that would be assembled into a composite skeleton, although he did claim it came from one individual, that he called Hydrokos, Water King. In 1845, you could pay 25 cents and go and see this giant sea serpent that Koch described as being 114 feet long and weighing 7,500 pounds. As I said, showman. Despite great skepticism from the scientific community, Hydrokos was a great hit and would eventually tour Europe like a rock star. The Smithsonian has quite a long history with Basilosaurus too. In 1894, George Brown Goode, then curator of the Smithsonian's National Museum, sent one of its assistant curators of invertebrate paleontology, Charles Schuchert, to Clark County in Alabama to collect basilosaur specimens. I wonder if they were just getting fed up with all the attention Hydrokos was getting. Apparently, Basilosaurus fossils were so common in Clark County that farmers had been using them in stone walls. He collected fossils from various individuals and assembled a complete skeleton that was the first accurately assembled Basilosaurus in the world. You can view it in all its glory today, along with other examples of whale evolution, in the wonderful Sand Ocean Hall in the National Museum of Natural History. Basilosaurus was the first completely aquatic whale. Collectively, these species belong to a group that are called the Basilosauridae. They were a diverse group, with the basilosaurs themselves at around 60 feet long. These large whales probably occupied the role of top predator in the Eocene oceans between 40 to 34 million years ago, feeding on fish, sharks and smaller whales. It was an odd-looking whale though, kind of eel-like, but not quite the sea serpents of Koch's imagination. The vertebrae of Basilosaurus were hollow and possibly filled with fluid, which meant it probably didn't have a deep dive capability and hunted mostly in surface waters. These Eocene monsters also had fairly small brains, meaning that, unlike modern whales, they probably didn't exhibit much complex social behaviour. It's thought that a group within the Basilosauridae, the Dorodontids, would give rise to modern whales. They were much smaller than the elongate basilosaurs at about 16 feet long, but had overall proportions resembling modern whales. It is from creatures like this that we get the diverse forms of all today's whales. Whales today are broadly divided into two groups, toothed whales and the baleen whales, who share a common ancestor around about 34 million years ago. Toothed whales, as their name suggests, are characterised by having teeth, and they hunt using echolocation by making a series of clicks at various frequencies. They range in size from the tiny 4.5-foot vaquita, a species of porpoise found in the Gulf of California, to the sperm whale that can range in size from 33 to 66 feet in length. They are also among the great acrobats of the oceans, as anyone who has watched dolphins surfing in the wake of a boat or seen orcas breaching out of a clear sea can attest. The other group of whales, the baleen whales, gulp large volumes of water and sieve out krill, small fish and other microplankton by squeezing the water back out through their baleen plates, a substance composed of a protein similar to your fingernails. Humpbacks are a popular favourite with whale watchers, but it is another species of baleen that is possibly the largest animal that has ever lived, the blue whale. At almost 100 feet long, the size of this animal is truly mind-blowing, especially when you consider that the main source of food is krill, tiny crustaceans, 0.4 to 0.8 inches long. Let's just pause here and consider the changes we have described. From the first terrestrially adapted cetaceans like Pachycetus at 50 million years ago to the first obligate aquatic members of the whale family such as Basilosaurus at around 41 million years ago. It took just 9 million years of evolution to radically transform this group of mammals. It shows how rapidly natural selection can operate when a group of creatures radiate to fill a relatively unoccupied niche. In this case, a niche left vacant by the giant Mesozoic reptiles following the end Cretaceous mid-extinction event. It also highlights how paleontology can be used to test the predictions made by evolutionary biologists, the fossils themselves being the acid test of our suppositions regarding our understanding of the history of life. By the time we examined the whales at Cerro Baena at around 6 to 9 million years ago, modern-looking whales had already evolved back in the Eocene. A whole range of marine mammals are found at the site, including 2 species of phoquid earless seals, and Odobenocetops, a bizarre-looking walrus-faced whale that had tusks. There was even a semi-aquatic sloth that probably grazed on seaweed and seagrass. But it is the fossil baleen whales that are probably the most spectacular. Dr. Nicholas Pyenson and collaborating scientists from Chile uncovered a fascinating fossil conundrum. Why are there so many fossil marine mammals present in this location, and why, given that under normal circumstances these creatures would be scavenged and their bones scattered, why are there so many in such an excellent state of preservation? What's more, this is not an isolated event. Similar collections of fossils at Cerro Baena are found in multiple, discrete horizons. It would appear that whatever killed and stranded these marine creatures happened around 4 times over a period of 10 to 16,000 years. Other features of this fossil deposit have helped unravel this mystery. First, these creatures were stranded on a tidal flat, roughly orthogonal to current flow. The whales are also preserved belly up, suggesting they died at sea and then were washed ashore. In addition, high concentrations of iron in the sediments hint at a high algal concentration in the waters in which these animals were swimming. It is thought that this all adds up to a story of a mass stranding caused by a harmful algal bloom, or HAB. Not all blooms of algae are harmful. In this image, you can see a bloom of coccoliths off the coast of Cornwall, England, during the summer of 1999. But some species of microplankton, including species of dinoflagellates and diatoms, can cause problems for marine life and have been known to cause whale strandings. Our story likely starts with rainfall over the Andes, flushing minerals rich in iron to the Pacific Ocean. This, in turn, causes a bloom of algae and the death of many marine mammals and fish. A high tide would help wash the animals ashore onto a mudflat, all belly up as the decomposing gases start to swell the gut. The ocean hydrodynamically aligned them into neat rows, producing a stranding, just as we find in modern whale strandings today. Usually, these whales would be scavenged by creatures living on shore, but back then, as today, a desert existed inland along the coast, restricting the number of creatures and potential scavengers living in the area. Sedimentation rates were also fairly constant, ensuring that the dead were covered rapidly. As such, Cerro Baena has provided scientists at the Smithsonian's National Museum of Natural History with a wonderful window into marine mammals of the Pacific Ocean over 6 million years ago. But more than that, it speaks to the fantastic evolutionary journey of this group of mammals, and also the incredible diversity that can result from natural selection in an instant of geological time. It has also shown how traditional excavation techniques, hand in hand with modern visualization technology, can help preserve and decode complex paleontological sites. Although the fossils are no longer visible, the site is preserved forever and will continue to provide valuable insight into the ecology and evolution of cetaceans for many years to come.